K nearest neighbors is nice because you just define your own distance function. You can deal with any kind of data. It doesn't really matter. As long as you can define a distance function, you're happy. You can have any kind of label. I mean, it could be categories like bench or chair, or it could be numbers like 2.6 or 3.5. I mean, K nearest neighbor with numbers is cool. I mean, if you end up so that your 3 nearest neighbor, so that like if you're doing 3 nearest neighbor, you could then take the average of their labels if they're numbers, maybe, or weight it according to how close you are to each of the nearest neighbors and get a weighted average of their labels as your prediction. You can do cool stuff like that. So very flexible, incredibly memory hungry, incredibly slow, unless you do fancy data structures, and even then it's kind of slow. Neural net's incredibly fast. You just, I mean, especially this linear thing, you just have some weights. You multiply the input, you're done. But all the inputs have to be numbers. All of the output has to be a number. Now you can choose 0 and 1 for your outputs if you're trying to train the classifier. So that's what I suggest you do for the assignment 5. We talked about inductive logic programming a long time ago. But it was the same kind of thing where there's some hypothesis space. It's not linear functions or Voronoi cells. It's like horn clauses. You're trying to build a horn clause that correctly deduces the stuff you want. But you can see it's the same. You have a hypothesis space. You're trying to learn something. You have training data. So this is where we are so far as far as supervised learning goes. Okay, input layer, hidden layer, output layer. One of the inputs is always going to be 1. Therefore, the weight on this coming out of here is going to be like the constant in a linear function. If we were just doing simple, basic linear regression, we just have 2 layers, and this cell right here might be the output, and it's a weighted sum of all the inputs. But if we do that, we're limited to linear functions. If we want to go nonlinear, then we go with a 3rd layer, and now this is the output. And the inputs all are weighted here, and then they go through a sigmoid function, which means that the value of this hidden unit will be pretty small until these values all get up to a certain threshold, at which point the output of the hidden unit will be much larger. And then those outputs from the hidden units are summed together and weighted. So there's a whole other set of weights here. And then we have an output. Does everyone understand the architecture of this is called an artificial neural network, an ANN, a 3-layer ANN. This is the classic neural net thing. So that's a neural net. I think I have a picture in the slides that tries to give you a sense of why the nonlinearity could be important, or how you get it. So if I have one hidden unit that gives me a sigmoid, this is right out of your textbook. One hidden unit gives me a sigmoid. I should use a piece of paper. One hidden unit gives me a sigmoid. It'll go right like that. Right? That'll be the response. If I have another hidden unit where the weights are all negative, right, I'll get the inverse response like that. If I sum these together, I'm going to get something that looks like that. Right? So the sum of nonlinear functions gives me this bump. And the picture from the book is illustrating a 2-dimensional bump. So we've got x1 and x2, and then the output is the vertical axis. And depending on how these linear functions are aligned, this bump is going to go in a certain direction. And then if I combine multiple bumps together, I'm going to end up with a single centralized tower here. So, and I can combine these to represent anything, any function. So you can see how the nonlinearity in the hidden layer is really important in increasing the expressive power of this predictor. Right? So then the magic question is, okay, given I have some training data, how do I learn the right weights to get the right kind of thing to come out? And the answer is nobody knows. For linear regression, it's easy. You use MATLAB and do the matrix algebra, or you use the online LMS procedure that I talked about last class. You're guaranteed to get the optimal solution. For neural nets, there's no training method that's guaranteed to give you the optimal fit of the network. So what do? I mean, people use neural nets every day. What the hell are they doing? They are doing local search. They're doing gradient descent, and there's a procedure called backpropagation of error, and it's not guaranteed to converge to the optimal weights. It is guaranteed to converge, but the solution you converge to is not guaranteed to be the optimal setting of the weights. So I'm sorry about that. But that's what you get if you want to use a neural net. This is one reason I strongly urge you not to use neural nets in the real world, because if something goes wrong, you're screwed. With linear regression, it's very easy to debug, and you know you have the optimal training, and it's very straightforward. But anyway, just so you know how neural nets work, one thing people do is you run BackProp a whole bunch of times from different starting configurations. And it'll converge to something that might be a local minimum, and you take the best local minimum you found. And that's better than just taking the first one. Lee?
When you say neural nets, how similar are they to neurological, physical, biochemical nets in my brain? Like when you say, there are problems with it.
Dude, this is what's in your brain. This is what's in your brain.
Yeah.
This is a neural net. How similar do they look to you?
They're both blue.
Yeah.
So
We're at UNH. Blue is the school color.
makes sense. All right. So they don't seem very similar.
These lines are very straight, and these are very squiggly, and they've got this cute little fringe things that these guys don't have.
Okay. All right. So
Plus, these guys have neurotransmitters, which I didn't draw.
huge bonus.
Exactly.
All right. Cool.
Any chemical interferes with your brain.
So there's no backwards error propagation in my brain.
Well, so, yeah, let's totally not get into that right now. Yeah, there are a lot of people that are very interested in figuring out how your brain learns stuff. And yeah, I'm not an expert on that. Every time two neurons fire about the same time, it's thought that their synaptic connections grow stronger. Anyway, so how do we train a neural net? So we want to learn one of these fantastic nonlinear functions. I mean, it's very cool it can learn a nonlinear function. In fact, someone has proven that if you use infinite precision arithmetic in implementing a neural net, that they're Turing complete, like they can compute any function, which is kind of amazing. So they are kind of cool. So how do we learn? So, oh crap. Let me just briefly, does everyone remember when we did a linear regression? We ended up with these update rules, right? So we're predicting y as a linear function of x. If you took multivariable anything, you could think of this as a matrix and that as a vector. If you don't like that, then you could just think of these as two single numbers. And the update rule was to look at the error and update our parameter. And if we had, that was supposed to be a 1, x1, x2, then these were the updates. And here's the error in our prediction. Like that was our prediction, that was the true value. This is the error, that's the learning rate. So if our prediction was too big, this number will be positive. This is a number less than 1 and greater than 0. So this is a small positive number, and we subtract it. So if our prediction was too big, it will now get smaller. And we do this all along here when the response was linear, when we have the prediction is x1 times theta 1. Then here, this is the update. What's the error? How big was x1? Learning rate, subtract it off to do the update. This same thing is going to come up with BackProp. So BackProp was actually invented in like the 60s, and no one really cared. And then it was reinvented in the 80s and caused this incredible explosion of interest in neural nets. if you have a net with k inputs, j hidden units, and I outputs, so it would go kji. Here's the error that we see. This is the derivative of the activation function. So this is the same. This is just analogous. On the previous slide, we had the error times x1. And x1 was the derivative with respect to x1. So this is the derivative with respect to input I. So depending on whatever activation function you use, if you use a sigmoid, then this is like, I don't remember, it has an e in it somewhere, like 1 over e or something. And so then we just take the error and multiply it by the activation of hidden unit j, multiply by the unit learning rate, and adjust our weight. This is the weight between hidden unit j and output I. So in this last layer, the learning is very much like linear regression. Same basic thing. Too bad Jen's not here because she's implementing this for her final project. So this is very much like linear regression in the last set of weights. But now the big question is, okay, what do we do for the first set of weights? Well, the answer is exactly the same thing. You just take, these are the errors, the sum of the errors going out of hidden unit j, and you just multiply them by the derivative. So it's exactly analogous to this equation here. And then you've got the same equation here where, okay, this represents the error. Here's the activation of input unit k times the learning rate, update the weights. So it's very much analogous to linear regression. But the error is going back through the network. It's getting back propagated backwards. And so you update these weights. And if you set the learning parameter correctly, then it is guaranteed to eventually converge to something that might be crap. So that's BackProp. Does that make any sense to anybody?
So
Nathan?
it only really propagates 2 steps, right?
Yeah, because there are only 2 layers. Yeah, doesn't make any sense. Does this first part make some amount of sense?
The overall concept of it, the error getting propagated back 2 places, that makes sense.
Okay. Okay.
There's only input units and output, but a lot of the math, which is 1 by root.
Yeah.
So that's not
I'm not going to ask you to replicate backpropagation on the exam. I guess I want you to see that this looks a lot like the equation on the previous slide, which is the kind of thing that you really should be able to know. So did you get the previous one, the linear one? Okay, good. You're in great shape then. You're good. So everyone see that this looks like the equation on the previous slide and that this looks kind of like that? That's all I really wanted to make sure to get across.
So the similarity, you mean, is it gets an error, it modifies it a bit, and then...
Yeah, you're just going in the direction that's going to decrease the error.
Okay.
And that's why it's guaranteed to converge, is because every time you go through, it's going to shrink the error a little bit.
That I got.
Yeah. So you could imagine someone could maybe prove something like that, that if at every step you make the error a little smaller, then at the end, the error is going to be infinitesimally small, and if you go infinitely long, the error is going to be 0. Okay. Great. So that's how much I want to say. So we did talk a little bit about neural nets. They're great because they're very expressive. They're lousy because they're hard to train. And if you ever read a paper about neural nets, you'll notice that they say things like, here we are training our neural net. Look at the error going down. And they'll have things like 1, 2, 3, 4. And you'll be like, wow, okay, after 4 examples, you got error that low? And then over here on the edge, they'll have like times 10 to the 5th. Something like that. And then you'll say, wow, it took you 10,000 examples to get the error low. But then no, then what happens is they say this is called a training epoch, which is the number of times you have seen all of the training examples. So I just want to try to emphasize neural nets are hard to train. They take a lot of data. Whereas linear regression, you like do it and it's done and it's optimal and you can go home. Plus, when the thing doesn't work and your boss comes to you and says, you better make this work by tomorrow or we're going to lose the contract. If I show you this neural net with like weights everywhere, you're not going to have a clue what to do. Whereas if I show you a linear function, it's very clear who's contributing what and how to tweak it. It may be impossible to get it to do what you want, but at least you know where to blame. Whereas the neural net, it may be impossible to get it to do what you want, but because these things are going in here and getting non-linearly combined, and then they're added together with these other non-linearly combined things, it's very hard to know who to blame if this output is too high for some reason on some particular example. So it's very hard to debug. So that's why if you want the high order bit of my opinion of neural nets, it's stay away.